Greetings. Welcome to Electronic Circuits 1. I am Razavi, and this is lecture number 32. Today we will look at the MOS device in more depth and understand one of the interesting second-order effects that occurs in this device and how that translates to the device characteristics. First, let's look at what we did last time and remember the equations that we derived for the MOSFET. So last time we went past this boundary here, and we allowed VDS to increase beyond VGS minus VTH. And what we observed was that as VDS becomes larger and larger, the depletion, the channel begins to pinch off near the drain end, meaning that the channel charge density begins to drop to 0. And once that happens, the current that we calculate by integrating along the channel comes out to be constant, assuming that that pinch-off point doesn't move much inside the channel. So we saw that now we can identify two regions of operation for the MOS device, depending on whether VDS is greater than this magical number, which we call the overdrive, or less. So if VDS is less than this value, we are in the triode region, and if it's greater than this value, we are in saturation. We saw that in saturation, the current doesn't change with VDS, so this drain current is constant even though this VDS changes. So if you put this in a black box, it looks like a two-terminal device, again not worrying about the substrate and body and all that, and we see that it operates as an ideal current source, which means it has a constant current. So in this region, so long as we guarantee that VDS is greater than that value, the device can be approximated by a current source. So that's good. That's what we were hoping to achieve when we built a little amplifier and then said, can we build a voltage-dependent current source? Indeed, we have a current source. And it's voltage dependent because its value depends on this guy. So it's important not to confuse this voltage with this voltage. This is a current source as far as these two terminals are concerned because when this voltage changes, this current doesn't. But it's a voltage dependent current source, meaning that if I change this battery from 1 volt to 2 volts, I get a new current source, and that new current source is also constant. Okay. And we saw that in saturation, the relation between ID and VDS is fixed. ID is constant. It doesn't have dependence on VDS. But we still have a relation between ID and VGS, obviously. Because as VGS increases, we increase the density of electrons in the channel, so we have more current capability. And that is reflected in this equation. So this equation tells us ID as a function of VGS. It doesn't have dependence on VDS, as we see over here. So in our circuits in this course, we are mostly interested in MOS devices operating in saturation. So in saturation, we say the current is constant, maybe relatively constant, as we will see shortly, as VDS changes, but it's a function of VGS. And it's a quadratic function of VGS. So if VGS is equal to VTH, meaning at one threshold, the device is right at the edge of off or on. And then as VGS exceeds the threshold, in proportion to the square of the overdrive, the current increases. All right. Today we want to look at this characteristic a little more carefully and see if it is really as ideal as I portrayed it to be. So we will talk about channel length modulation, which is one departure from that ideal behavior that we saw. And then we will approach the concept of biasing, a very important concept that is necessary in many types of circuits. So let's begin with channel length modulation and see what this is about. Now, if you are familiar with bipolar devices, this is similar to early effect in bipolar transistors, but I will assume that you're not, so we'll just start from scratch and talk about it. All right, so when people built MOSFETs for the first time and measured their ID versus VDS, the first surprise was that ID did not follow a parabolic behavior all the way, as we saw before. So it started as a parabola, reached here, the maximum, but then it didn't fall. We said that it went and stayed constant. Okay. But when they looked at this very carefully, they saw that this is actually not quite constant. So in reality, if I change the color to something else, what we see is that this keeps going up by some small amount as we increase VDS. And it's almost a straight line. So it goes up as a parabola, and then from here on, almost like a straight line, it keeps increasing. So the question is, why does this happen? Well, again, we have to go inside the transistor, see what's going on, and maybe we understand this phenomenon. So let's draw the transistor again, apply our voltages around it, and see what we get. So the source is grounded, the gate is connected to a battery. So this is the setup that we have here. This drain is connected to a battery, and we have some channel, and because we are in saturation, there's a pinch-off point, right? So somewhere around here, the channel is pinched off. So that's the channel. We have lots of electrons around here, and fewer as we go this way. A density of electrons. Okay. All right, so as VDS increases, now let's assume that the source is 0, so we just increase the drain voltage, right? As the drain voltage increases, what happens to this pinch-off point? Well, if you remember last time we said that because this voltage is higher, this point has to move back a little bit. Because this point happens where the voltage difference between the gate and the local potential is one threshold. So if I increase this voltage, which means in this vicinity I'm increasing the voltage, this point has to go back. The pinch-off has to happen at a shorter distance so that the voltage difference between these two is one threshold. So in other words, as VDS increases, the channel length actually decreases. The channel length is defined as the length of the channel from here to here, right? The channel length decreases by a small amount. So before we said let's assume it doesn't change, and that's how we got a straight line. But now we are considering that second order effect. So what happens if the channel length decreases? Well, if we go back to our integration, now we have to integrate from 0 to L, but this L is not the original L, right? For some drain voltage, we had L over here. For a new drain voltage, we have L over here, and so on. So the L that appears eventually in our equation, as you remember from here, in this equation, slightly decreases as the drain voltage increases. So we lied when we said ID does not depend on VDS, right? We said this is straight. No, what really happens is that as VDS increases, L slightly decreases, which means ID slightly increases. And that's what the phenomenon that we see. So that is the situation. And the question is, how do we model this so that it is manageable in our calculations? Do we really want to put an L in the denominator and make it a voltage-dependent quantity? That's a little messy. So instead, this is what we will do. We'll make an approximation. So we say ID is equal to 1/2 of mu n C ox W over L. L is the original L, the effective L from here to here. Okay, that's the L that we use here. Now, if the higher drain voltage pushes the pinch-off point to the left, I will take care of that not in this L term, but somewhere else. So I will write everything else like before, and I will have a correction factor to reflect this behavior here. So what should the correction factor look like? Okay, so we need VDS. That's for sure, right? As VDS goes up, we want the current to go up. All right, but it cannot be just multiplied by VDS, because that means that this creates a very strong relationship like this. We just want to have a mild relationship like this. So we have to add some constant to VDS, and then we have some sort of coefficient so that the units are right? This is 1, has no dimension. This has to have no dimension, so lambda is 1 over volt. So this correction factor tells us that, yes, as VDS increases, this begins to increase, right? Lambda is some number. So lambda, which has a unit of 1 over volt, is called the channel length modulation coefficient. And this phenomenon is called channel length modulation. The length of the channel is modulated as the drain voltage goes up and down. So now we have a very simple model with this extra coefficient here to represent this behavior, right? So that's pretty nice. It's not that complicated, and it allows us to see what happens. Now, this tells us that in saturation, even though we are in saturation here, the current of the device, this device here, is not exactly constant as this voltage goes up and down, right? So we see that the current slightly changes. So it's not an ideal current source. It's an approximation of a current source, and that's something we have to remember. Now, when do we take this into account, and when do we not take this into account? It depends on the situation. So as engineers, our first reaction should be to use the simplest model possible. So when I see a MOS device, and I know by some calculations that it's in saturation, the only thing I consider is first this, right? And then I go along and see where I end up. If the results are not very sensible, then I have to trace back and say, well, maybe channel length modulation is important, as I should include that. Okay? All right. So with channel length modulation, we have this behavior for the device. And let me see if there's anything else I want to mention about this. So I can still redraw the model of the transistor that we did last time. We drew last time. We said the device has a gate, a drain, a source. Between gate and source, we don't have really any current. The gate is insulated from the rest of the device. In some modern devices, we have a bit of leakage between the gate and the channel, but we don't worry about that. So it's an open circuit. There's no current flowing through it at low frequencies. So we just say what we have here is VGS. And this current source is the current that flows from drain to source. And its value is given by some amount if we know we are in saturation. So if we know we're in saturation, this is the equation that we have. So we have 1/2 of mu n C ox W over L VGS minus VTH squared 1 plus lambda VDS. This is a more complete model of the MOS transistor that we can use. If you are given a MOS device, usually you are given mu and C ox. Then W and L are things that you can choose if you want to design the MOS device. You pick some W, some L. And lambda is also a known quantity for the technology at hand. So lambda is also a known value. Okay, this is what we call channel length modulation. And in our calculations from now on, sometimes we include this, sometimes we don't, depending on the accuracies that we are looking for. So if I write lambda equals 0, that means channel length modulation is neglected. And those of you who are familiar with bipolar devices see the resemblance between this behavior here, channel length modulation, and the early effect in bipolar transistors. Okay, all right. In the next step, we want to talk about the concept of biasing. Again, this is something that we talked about extensively in bipolar circuits, but I'm assuming that you haven't watched those necessarily. So I'll start from the beginning and talk about why we need biasing. All right, so let's take a step back and remember what we did before introducing the MOS device. We said we want to build an amplifier. So let's do that again. So let's go ahead and try to build an amplifier. Because I have a device that I can buy that can serve as a voltage-dependent current source, right? Now, this is nonlinear, so that might worry you, but for now, don't worry about it. Okay, it's a voltage-dependent current source. So if you remember, this is what we did before. We said, I buy a voltage-dependent current source. Now, previously, I didn't connect these, doesn't matter really. We said that this voltage current source says, if you give me V1, I give you K V1. Right? That was the voltage-dependent current source that we used. And we said, well, if you pass this current through a resistor to obtain a voltage, so here's the voltage, and we give it a voltage, an input voltage, some sort of maybe a sinusoid, right? For example, my voice going into this microphone, and my voice is not a sinusoid, but let's say a sinusoid. Then what we expect is that V out becomes proportional to V in. In fact, if you remember, V out was equal to minus K times RL times V in. And if KRL, this constant times this RL, is large enough, we have amplification. Let's say KRL is 10. So if we have a 1 millivolt swing here, we get a 10 millivolt swing at the output. And that's amplification. Now we have a voltage-dependent current source. So let's go and build an amplifier out of this device. All right, here it is. We have our voltage-dependent current source like this. I'll just copy everything down here. So I have RL. And then I have an input, for example, from a microphone, right? So I will draw a microphone signal, a microphone symbol here, mic. And again, this microphone signal looks like this. It has a signal that goes up and down like this. And it has some amplitude, some peak amplitude, let's say 5 millivolts. Just as an example. Okay. Now the microphone signal starts from 0, goes up by 5 millivolts, and goes down by 5 millivolts, around 0. Okay. So do we have an amplifier here? Well, let's look at this transistor here. And in particular, let's look at VGS. Now, what we do know from this type of characteristic is that if a device is in saturation, ID versus VGS has this behavior. We don't have any current up to one threshold, and then beyond that we have a square law behavior according to this equation. Now, in all of these calculations, we'll assume lambda equals 0 so that we don't have to worry about that too much. All right, so with this setup, I'm hoping to build an amplifier. But if I look carefully, something is not quite right. The microphone signal perturbs this VGS from 0 to 5 millivolts, plus 5 millivolts, or from 0 to minus 5 millivolts, right? So on this characteristic, I'm right here. VGS goes up by 5 millivolts or goes down by 5 millivolts. How much ID do I have? 0. The device is off. The device is dead. So this circuit cannot possibly be an amplifier because the voltage coming from the microphone is not capable of creating any significant current or current change in the MOS device. So I hope that's clear. All right, so if the signal is 5 millivolts and the threshold is, let's say, 0.5 volts or 0.3 volts, obviously the device is never turned on. Okay, so we'll call this first attempt in our amplifier construction endeavor, and that was not very successful. So what should I do? Well, the problem is that this signal is just way too small. The device is not turned on at all. So maybe what I should do is add something else to this signal so that even when there's no signal, this device, this transistor has some life in it, right? And by that I mean this. So let's go to our second attempt. And why don't I do this? Let's try, we have the microphone, still producing that type of signal. I come along and place a battery here. And I pick this battery voltage to be 1 threshold. And I still have the rest of the stuff, resistor and all that. And now I would like to see what happens. Okay, now, is the situation better? Well, maybe, but is it good enough? So let's see. Well, if you look at this carefully, we see that now, if the microphone is quiet, so if I'm not talking to the microphone, then there's no signal. The signal is 0. So the voltage difference between these two is 0. That means that VGS of the device, in the absence of a microphone signal, is equal to 1 threshold. So we are right here. Okay? Now, the signal comes in, the microphone signal comes in and raises this voltage by 5 millivolts. So we have this much plus 5 millivolts, right? So we go over here. So this is a VTH plus 5 millivolts. Okay. And we get some current. So is that a good scenario? Can we use this and build an amplifier? So I'll just give you some example numbers, some representative numbers to see what we end up with, right? If the numbers are okay, sure, we have an amplifier. If not, then we have to go and go to a third attempt. All right, so as an example, like last time, let's assume that mu n Cox is 100 microamps per volt squared. W over L is 10. And the threshold is, for example, 0.5 volts. It doesn't matter too much. And you would like to see how much current we get when VGS is VTH plus this much, plus 5 millivolts, right? The microphone raises its voltage by 5 millivolts. Okay, so then we can write ID is equal to 1/2 of, so I'm writing this equation without the correction due to channel length modulation. So 1/2 of mu n Cox, so 1/2 times 100 microamps per volt squared times W over L times 10 times, what goes in here? VGS minus VTH. VGS is this much, VTH is this much. So we are above VTH by 5 millivolts. Our overdrive resulting from the microphone signal is 5 millivolts. So 5 millivolts squared. And calculate this, what do we get? We get 12.5 nanoamperes. This current looks awfully small. And we will see what we mean by small. Okay, so if the current increased by 12.5 nanoamps, when the microphone signal rose by 5 millivolts, then I can pass this current through a resistor to have some sort of voltage, right? That's how I'm trying to build an amplifier. Okay, so how much RL should I pick to have some reasonable amplification? So again, let's look for an amplification factor of 10. So from 5 millivolts, I'm hoping to build 50 millivolts, right, at this output. So I'm hoping that at the output, I will have a swing like this. Well, it's actually inverted, but it doesn't matter. And I'm hoping that this peak will be 50 millivolts, right? Okay, so this current at 12.5 nanoamps has to pass through RL and give me 50 millivolts. So I can find RL. So RL is equal to the voltage that I need, 50 millivolts, divided by the current that the transistor has produced, 12.5 nanoamps. And that comes out to be 4 mega ohms. 4 mega ohms. And that's a very, very large resistor. So we could buy a 4 mega ohm resistor in discrete form, but we don't want to build an amplifier like that. That amplifier would not be very good. All right, so something is not quite right here. Even though we added a voltage, we brought the operating point from here, where the transistor was totally dead, to here, where the transistor is partially dead, right? So can I improve further so that I don't end up with such a small current here? Well, maybe what I should do is, instead of operating at this point, and when the signal comes in, I just go up here, maybe I should start somewhere around here, so that when the signal comes in, I go farther in the current domain. So let me elaborate on that. I need to add a page, and we'll see how that comes about. All right, so that's our third attempt. And here's what we're thinking. We take the transistor, we have our good old microphone here, and then on top of that we have a voltage, and this voltage is actually more than a threshold. So we'll call it V0. And then of course we have our resistor, RL, and so on. And what we are thinking is this. If ID versus VGS, we have nothing up to one threshold, and then we have something like this. What if V0 is over here? So now the microphone signal comes in. It comes in, and this VGS is now modulated, so to speak, right? So in the absence of a microphone signal, when this difference is 0, VGS is equal to V0. When the signal comes in, VGS goes up a little and goes down a little. Let's say by 5 millivolts this way and 5 millivolts this way. Okay, so we can do a quick calculation and see if the situation has improved now that this battery is chosen to be somewhat above the threshold voltage. So as an example, I chose V0 to be 0.9 volts. Remember that the threshold was 0.4 volts, right? 0.5 volts. So VTH is 0.5 volts. Okay, so what I will do is this. I will calculate two quantities. First, no signal. If there's no signal, we have this much battery, and we have a certain current. How do we find the current? Just like this. We have an equation for that current. We'll call this ID0. In the second step, I allow the microphone signal to come in and be added to V0. So VGS goes from V0 up by 5 millivolts. So we go over here. We go up by 5 millivolts. Let me erase that for now. We go up by So this is V0. We go up by 5 millivolts. And then we get a new current, ID1. And then we want to see, as we went from here to here, how much increase did we see in ID? Maybe this is better than the previous situation, and maybe the value of this resistor will be more reasonable. Okay, so we calculate ID0. ID0 is again 1/2 of mu n C ox. So 1/2 of mu n C ox W over L. VGS, how much is VGS? V0, no signal, so V0 is 0.9 volts. 0.9 volts minus the threshold, 0.5 volts squared. And that gets us approximately 80 microamps. So we have 80 microamps of current. So when there's no signal, we have a current of 80 microamps flowing from drain to source. And we have a gate source voltage of 0.9 volts. Now the signal comes in, it perturbs things. So it perturbs VGS by 5 millivolts. So VGS now goes to 905 millivolts. All right, so then ID1 is calculated as all of this. Here is 0.905 volts minus 0.5 volts squared, right? And this gives us 82 microamps. So we have 82 microamps. Okay, so the current through the resistor increased by 2 microamps when the microphone signal came in and raised the gate source voltage by 5 millivolts. So what kind of resistor value should I choose here so that I get a swing of 50 millivolts at the output, like before? All right, so we say change in ID is equal to 2 microamps. You realize why we look at the change, because this 80 microamps was with no signal. This is with the signal. So the difference between these two indicates how much signal has come in and been amplified and so on, right? Okay, so 2 microamps. And that means that if I want to obtain a 50 millivolt swing from these 2 microamps, I have to divide that by 2 microamps, and that gives me 25 kilo ohms. So the resistor value is much more reasonable than before, right? Before we had how much? 4 mega ohms. Now we have 25 kilo ohms. So that's much more respectable. All right, so this tells us something very important. It says if we want to use a MOS device, for example, as an amplifying transistor, then we can't just bring the signal in and give it to the MOS device and hope that something will work. First, we have to set up some conditions around the MOS device even before the signal comes in. And those conditions are called biasing, bias conditions. For example, we have a certain battery between the gate and source so as to create a certain VGS over here and a certain amount of current. So even when there is no signal, the device has a certain VGS and a certain drain current. Those are called bias quantities. And in fact, this point is called the operating point. So we see that need to bias the transistor by applying, maybe I should say creating by creating proper current and terminal voltages. So current inside the device and voltages around the device, the gate and the source and the drain and so on. So maybe I should say voltages in the absence of signals. Okay, so when there's no signal here, we have a certain VGS, this much, we have a certain current, this much. So those are proper current and voltages. And the reason for this is that, so that the device can amplify the signal. Okay, so we know that a signal will come in at some point, but before the signal comes in, we have to set up proper biasing. And this point is called the operating point. Okay, so as you can see, biasing is a critical issue. Without biasing, the transistor is dead. Doesn't have any ability to do anything. So we do need to have some bias currents and voltages around the device before the signal comes in. This is a question that we always ask students in different classes. Why do we bias transistors? And sometimes, oftentimes, they don't really have a clear answer for it. So to make them work. But what do we mean by to make them work? So what we mean is we have created the proper current and the proper voltages so that the device is capable of amplification. All right, that's something if you can define as why we bias transistors. Okay, so let me look at the following. All right, so let me make some observations before we wrap this up. All right, let's change the color. So, observations. Okay, so number one, what we have seen is that the MOS device can operate as a voltage-dependent current source. So we give it a voltage, it gives us a current. Such a device is also said to convert a voltage to a current. Okay, so we say a MOS device converts a voltage to a current. In fact, we might call it a voltage to current converter. So you say a MOS device can be considered a voltage V to current I converter. So that's how we sometimes look at it. It's a voltage to current converter. We give it a voltage, you get a current. Of course, it's nonlinear, various things, doesn't matter at this point, but that's what it is. Okay, and a voltage to current converter has another name in circuit design, which you should also know, and that is called a transconductor. So sometimes we say a MOS device is a transconductor. And these are all fancy names for what it does, right? It just converts a voltage to a current. It's a voltage-dependent current source. Okay. All right. Now, based on this, let's see. I would like to make another observation, so I will write it here. So which operating point is preferred. Here are two scenarios, and I want you to tell me which one of these is preferred, ID versus VGS. So we have a device in saturation, so always in saturation unless otherwise specified. So we have a device in saturation, and what we see is this general behavior, right? Okay, so I choose one operating point to be here. So let's call this V1. This gives us some current, I1. This is operating point number 1. Or I pick another one over here, V2, some operating point, and some current, I2. So that's operating point number 1. This is operating point number 2. Which one of these better and why? I'll give you 90 seconds to think about that. Okay, so what did you decide? Well, what we recognize is that this curve is not linear. It's a second order function, it's a quadratic function, which means the slope of this curve increases with VGS, right? Okay, so if I sit here and I apply a signal, let's say from the microphone, on top of this amount of VGS, this bias value, then I have a certain perturbation in the current. If this V changes by delta V, this current changes by delta I, and we know that delta I is equal to delta V times the derivative. Similarly here, if I change this by delta V, this current changes by delta I, and that delta I is given by this delta V times the derivative. So we see that the derivative is higher here than here. So for a given input signal swing from a microphone, for example, let's say 5 millivolts of swing here, we get a larger current change around this point than around this point. Because if that 5 millivolts is considered small, 5 millivolts of change here is multiplied by this derivative to give us this current change. And here, this 5 millivolts of change is multiplied by this derivative to give us this current change. And because the derivative is higher here than here, we have a more favorable situation here, meaning that a 5 millivolt signal coming in will give us a greater current change at this point than at this point. Meaning that the transistor, in a sense, is stronger here than here. It's a better voltage to current converter here than it is here. When we perturb this voltage by some amount, we get some current change from that perturbation. And over here, the transistor is stronger. For a given voltage perturbation, it gives us larger current changes. So the transistor is stronger here than here, so this point will be preferable. But does it come for free, or is there something, some price we have to pay? Well, yes, we have to pay a price. Remember that when there is no signal, right, you do not target the microphone, right, anything, we have a bias current, we have a drain current, and that drain current is draining the battery out. I have a battery in my transmitter here. That battery is being drained out because I am drawing a certain amount of current. So if I want to have a stronger device, so to speak, I have to go over here, which means I have more bias current, and more bias current will drain the battery more quickly. So that is the price that we pay for a stronger transistor. Very well. Now with these, we are ready to look at another interesting concept. But before we go there, I need to show you a few other skills that we use often in our analysis. And one of them is the following: combining time response with IV characteristics. This is not that hard. I just need to explain it to you so that from now on, anytime we use that, you're familiar with what we mean. Okay, so again, let's go back to our simple amplifier where we have a microphone and we have a battery and so on. Okay, and let's just focus on the drain current of this device, ID. We have some other stuff here, but we don't worry about that too much. Just ID, this current. Okay, so again, there's a certain bias. We call it V0. So here's what we have. We have ID as a function of VGS, no current up to one threshold, and then some behavior like that. And V0, the bias is somewhere. So let's say this is V0. And we have a certain amount of current, ID. Okay. Now, the signal comes in. Where I'm talking to the microphone, the signal is coming in. The signal, let's say, is a sinusoid. So let's draw that sinusoid here. So this is V mic, and just a simple sinusoid like that as a function of time. All right, now I can see things better if I try to combine this plot with this plot. So let me explain what that means. Okay, so what I will do is I will rotate this by 90 degrees clockwise. So I get this. So that's V mic, and this is the signal, and this is T. So far so good? Okay. Now I realize that V mic, this voltage, is added to this battery voltage, right? So let's go and add it to the battery voltage. Then what do we get? So I will plot V mic plus V0. So what does it look like? Well, it's just shifted, right? So this is 0 for both time and voltage. And now we are over here. So we have this. And it starts at V0 here. That's okay, right? I'm just twisting your mind a little, but that's what we get. You could have drawn this here, shifted this by V0, and then turned by 90 degrees, but that's what we have. All right, so this axis is this whole voltage here, VGS, because it's V mic plus V0. And this axis is time, and this voltage is going up and down around V0. Now let's take this and put it right on the bottom of this curve here. Okay, so here's what we have. This axis is actually VGS. So we just write VGS. And this waveform is swinging around V0. So there's a V0 right here. So this voltage is swinging around V0, and this axis is time. Okay, so the important point here is that this axis happens to be the same as this axis after all of these manipulations. All right, now what I would like to do is try to plot ID as a function of time. And this combining allows me to do that. So if I change the color of my pen, you can see how that is accomplished. So I say, well, VGS has gone from V0 to some amount, V0 plus 5 millivolts, right? Okay, so that comes up here and maps to this amount of current. So when the gate source voltage starts from V0 and goes up by 5 millivolts as a result of the microphone signal, the current starts from its bias value. So this should be I0, by the way, and it goes to some new value. Okay, and how about when the microphone signal goes down? So we go below V0. No problem. So now the new VGS is this much from here to here, right? So that comes up here and maps to another value. So now I can go ahead here, draw ID as a function of t. For this peak, I got this much current. So that's the current that I get here. For this peak, I got this much current. That's the current I get here. And in between, I have something in between, right? So that's the approximate behavior of the drain current as a function of time. We know that if the gate source voltage is changing periodically, the drain current also has to change periodically, so that makes sense. Now, what is the exact shape of this? Is it a sinusoid, etc.? We don't know, but at least qualitatively, we have a picture of how ID changes as a function of time. So this combining of the time response of the input with the IV characteristics to get the time response of the output is very useful and is handy in our calculations and analyses. Very well. Okay, let's talk about one more interesting concept today, which is critical in everything that we do from now on. And for that, I would like to go back to this example that I showed you before. We said that the second operating point is preferable because this characteristic has a higher slope here. And that higher slope signifies a stronger transistor, because for a given signal change here, like this kind of thing, right, we get a larger change here, like this kind of thing. So this type of swing is larger around this operating point than around this operating point. So perhaps we can define a quantity that tells us how strong a transistor is. And what we are thinking is maybe just the slope of this curve tells us how strong the transistor is, right? Here, the transistor is very weak, because when we increase the gate source voltage by 5 millivolts, we got only 12.5 nanoamperes of current. So the voltage to current conversion of the device was very weak. 5 millivolts of change gave us only 12.5 nanoamperes of current. Later on, we went to 0.9 volts and things were better. 5 millivolts of change gave us 2 microamps of change in the current. So voltage to current conversion was better. The transistor was stronger. And of course here the transistor is dead because the slope is 0, so nothing there. Okay, so what we are thinking is maybe you can call the slope of ID versus VGS something, and use that to feel how strong the transistor is as far as voltage to current conversion is concerned. So we do that. We exactly define that. So let me go to the next page. And that's what we call the concept of Transconductance. Conductance. So a transconductor, like a transistor, has a certain amount of transconductance, just the way a resistor has a certain amount of resistance. Okay, here's what we are thinking. So we have ID versus VGS. And we go up to one threshold. Beyond that, we go up quadratically. And we define officially the transconductance, which we denote by G sub M, to be the derivative of ID versus VGS with respect to VGS. Okay, the slope of this characteristic is called the transconductance. You can see that the unit is either 1 over ohm, because this is 1 over resistance, or there's also an official name for this, which we say Siemens, and we denote it by uppercase S. Lowercase s is used for second, uppercase S is used for Siemens. So either way, whichever you like. So GM is lower here, higher here, and 0 here, right? So that's the transconductance of the device. And it tells us how strong the device is. We saw that we can have a higher transconductance, we can have a stronger device if we go farther and farther over here to have a larger amount of current. But then the penalty we pay is a larger amount of current drawing from the battery, so a shorter battery lifetime. All right, now because we have an equation for ID as a function of VGS in the saturation region, we should be able to calculate this GM. So let's go ahead and do that. ID is equal to 1/2 of mu n C ox W over L VGS minus VTH squared. Again, lambda is 0. And we just need to take the derivative of both sides with respect to VGS. So that's easy, right? This 2 cancels this, and we end up with a GM is equal to mu n C ox W over L times VGS minus VTH. That's very simple. This just tells us how the slope varies, right? So it says, if you were to plot the slope of this characteristic as a function of VGS, what would you get? Well, it says this. It says, if you were to plot the slope, GM, as a function of VGS, well, over here, GM is 0, no slope, right, up to VTH. And then beyond that, we have this simple straight line. So, boom. Right? This slope keeps increasing. So that's the slope of the characteristic. So if we bias the device here, we have a higher VGS, and we are still in saturation. That's the key. And then we have a higher transconductance. Right? That's what this equation tells us. Okay. Now, it turns out that there are 2 more equations for transconductance that I should mention here. The other one, the second one is this, 2ID over VGS minus VTH. This arises because I can take this 2ID and divide it by VGS minus VTH. And what I'm left over with is this. Right? So if you combine these two, you get this. And there's yet a third equation. So GM is equal to 2ID mu n C ox W over L. This is obtained if I go back here, I find VGS from here and plug it in here. So VGS is equal to ID divided by this whole thing, square root of that. And then I use that VGS minus VTH over here, and I find the new GM, and that's the new GM. So we have 3 equations for the transconductance of a MOS device. And it's very interesting because each of these equations tells us something about how GM varies with various parameters. GM varies with VGS minus VTH, yes. GM varies with ID, yeah, we saw that, right? We saw if we have biasing here, we have a lower GM than if we are biasing here. And then GM also varies with W over L, as indicated here and here, and also some interesting things. So these are things that we have to study in the future. But the transconductance of a MOS device, which tells us how strong the device is in converting a voltage to a current, has these three expressions for it. Okay, our time is up. I just want to mention one more point before we go home, and that's in relation to these amplifier designs that we looked at. For example, this one, right? That was our third attempt, and we seemed sort of happy with it. We said, yeah, we have 2 microamps of change in response to 5 millivolts of change. The resistor was 25 kilo ohms. Everything looked good. But one should ask, is this configuration such that the device is in saturation? We took care of the gate source voltage, right? We applied the battery here, chose it to be this value, and so on. And I just drew ID as a function of VGS. But remember, for the device to be in saturation, the drain source voltage also has to be some value, right? It cannot be too low. If it's too low, then we have a problem. How much is drain source voltage here when there is no signal? If there's no signal here, we have a battery between gate and source. But we don't have any battery connected to the drain. So then what's going on here? Looks like the device is not capable of carrying any current here in this loop. So maybe the device is actually not biased properly yet. So for that, you have to wait until the next lecture. I will see you next time.